Gives me 5 more minutes.
Nope, that's 5 minutes. Hold on, watch out.
Okay, here it comes. Good morning. Welcome back to the CMPS 2018 conference. My name is Bruce Nabby, and this is the start of the workshop we're going to hold called Superlight. What the Superlight workshop is it's not a presentation. It's involving all the members who are here at the conference involved in some scientific thinking. And the thinking being, you can assume that I will make a hypothesis or a statement as a student in the class saying, I woke up in the middle of the night and had this idea, and I need all your help to ring it out, so to speak. Find out, do you think it's true? Who's going to challenge it? What questions are they asked? We're working on this together. So let me, since I've labeled it also a paradox, let me go back to the twin paradox in relativity. Is there anyone who hasn't heard the term the twin paradox? So that I know I'm dealing with an audience who's okay, pretty much up. But I saw a lot of frowns when I was describing it for, so let's go back and be specific. So in relativity, Einstein, he made a serious language error, is my view, in using the word rest frame. And that's bothered people forever, where he starts out by saying, let's assume that there's one frame at rest. And then he talks about objects moving in the rest frame. And it's only later on, after he goes through that whole description and gets to the bottom of that theory, that he then says, but there was no reason for us to declare that rest, because it should be a relative principle that you could call either situation at rest and move the other one. And that's a hard concept for a lot of people to come with. So, and how, when he went to the press, or when the press got involved, they couldn't make that distinction. So the way you always hear it is, we are here on Earth, so I'm just going to draw, here's the Earth, and there are two twin brothers. And of course, this is always Bob and Alice. And Alice is one of the twins, and she gets in a rocket here, and she goes flying away. And she's gone for 30 years, and she comes back. And then, using Einstein's theory of time dilation, Bob says, well, when she arrives, she's going to be younger than I am, because she's been flying around at 0.6 C or something, 0.8 C for a while. She comes back, she's younger. And because the press always shows this from the Earth's view, everybody says, oh, okay. And that's what you'll see in all the movies and so forth. But scientifically, somebody says, well, what happens if Bob gets in the rocket and flies around? Well, then Alice says, well, Bob gets back, he's going to be younger than I am. But if you still have your brain that the one person's standing still and the other one's moving, this doesn't make sense. So it's still confusing. So the usual answer is to say, all right, Bob and Alice are born in a space station far out in space, away from any planets or anything. And they get in 2 rocket ships, and they both go flying around. We don't know what speeds they are, but they're both moving. But Bob measures the speed of Alice using light beams, and he concludes that Alice is moving at 0.6 C. So he takes his calculation and says when she gets back in 30 years, she's going to be 25 or 20, whatever the number is, depending on the speed. But Alice also does that calculation on Bob's rocket. He said, well, Bob's flying around with respect to me at high speed. So when Bob gets back, he's going to be 20 years old, and I'm 30. But when they get together for the reunion, we have a problem, which is a philosophical problem. Because they're going to walk up and shake hands and both give each other a hug, and both expect the other person is going to be younger. And you can't have both younger. It's a philosophical nightmare. So I want to go back and eyeball each one of you to get an acknowledgement that you all see from me that that's the twin paradox that science has been fighting with since Einstein wrote the paper, right? Well, anybody doesn't agree? Because it's okay if you disagree, then we have a language problem that we have to work out. Okay. The whole relativity thing is one of the hot buttons at the society. And if you go on and look at the email list, which I did for the last 3 years, it has 60% of the bickering without solution. And I try to bring it to some solution, and we're not getting to any solution. And my belief is it's primarily from language problems, not from math problems or engineering. It's just the basic, because a whole bunch of will get hung up on the rest if it's at rest. I mean, they can't let that go. All right, so here's the twin problem. And we started a special project called the GPS and Lightspeed project. I don't know if you all are familiar with it, but we did that as a formal project of CNPS, and it's been trying to work it out on the forum, not going well. Tried to pull together a team, and asked them to do three things, three assignments. One person had to work up the theory as if light came from a source and its speed was controlled by the source. The second group had to say light is controlled by an ether, and they had to pull together the mathematics for the ether. And the third group had to say, no, light is constant according to the observer, and they had to work up the math for the observer. All right. They get off into so many different problems of gravitational effects and so forth. We still haven't resolved those three basics. And the key was to make it a basic experiment for GPS, all right, which we did. And so the answer is pretty much known from GPS experiments. And it's a complex one, and it comes from our member, Ron Hatch, who produced the information. But from his analysis, he states light is controlled by an ether, not by the source, and not by observers, but it's controlled by an ether. However, the ether is entrapped around the Earth, and the measured drift speed of the ether over us right now is very slow. It's around 11 miles per hour. And measurably, within a few miles per hour, they have an error band. So he's got that in his mind. I heard some talk about people thinking that the relativity equations work and they can be programmed in, but they don't want to talk about them. And Ron tells us directly that when he was involved in the first launches of the first satellites, they employed corrections based on Einstein's relativity numbers. And they were off with errors like 7 to 20 miles. And they didn't work. And there was a big then ruckus among the scientists and what they were going to do, and they started fighting about their equations. And what the engineers did is they just ran down and said, we know the person's here, the GPS says they're there, dial in the correction. And they kept dialing different variables until they got it to within their 10 centimeter offset, which is the best that they could do. And they never talked to the scientists because that argument never settled down. But he has the data, and we have the data. And we're trying to get to the point where we're going to help settle this argument. Help. We're pretty sure we're not going to get to the end of it. All right. So you're both, we understand this problem, the twin problem, and if you want to get into any more details, just go onto the website and find Nick Percival's videos, because Nick of Time, I mean, he's a specialist in dilation and the twin problem, he's got that on. Okay, so I wake up in the middle of the night and I came up with this other idea. You know, I'm just making that up for how we should interact. And it's the following. What if we discover a new form of light? And it's not just the one we know, which is visible, but we jump out a little bit into the ultraviolet. I'm making this up, right? It's because it's going to lead to a theoretical discussion, not an actual measurement. So theoretically, we have this new light, and when we measure its speed, it's 10C. And we have these special instruments we can measure this to. Okay, so now we have this, and now we're going to go back and we're going to do our measurements in Einstein's using his equations, and we're going to take and we're going to have somebody in this rocket here, Alice again, and Bob is coming the other way. All the standard conventional things. And Bob has got his 1 meter rod here. And Alice has her 1 meter rod over here. And at the space station they measure them, they're the same, and then they take off. And then now Bob's flying along using light. This is the important part. Using light, Alice sends her signals up and they bounce off of mirrors and so forth. Alice measures that. And you guys can help me because I can't ever remember the formulas of them all the time. So, but anyway, so what Alice is going to say about Bob is the L length of Bob's rod is going to be 1 over gamma. L Alice. Is that right? I mean, maybe write these. The length in Bob's rocket equals length Alice 1 over gamma. Is that right, or is gamma on top? I don't know. Okay. But anyway, the answer is Alice measures Bob's meter rod and says it's shorter. He did something to play with it while they were flying, and it's now 0.6. And let's get specific about gamma, which is going to be root 1 over c squared minus v squared. Yeah, should have wrote that down. Here we go. That does that. Here's the paradox. Alice has this new measuring instrument that I talked about that uses superlight. And the superlight flies 10C. So the gamma here, and we will pick a number, but the gamma for C is 0.8. What's the gamma for superlight? Approximately, it's going to be approximately, I didn't do the math, but we're going to see, it's 0.08, right? It's 10 times slower. or is it squared?
V can't be greater than C in that formula.
No, oh, what I'm saying here is V is going to be the same. The relative velocity of these two is going to be the same. And
So you're changing C.
so, in one case you're using C, and the other one this is C, and the other one is S. Super light speed. Right. Super light speed, S squared minus V squared. Right? So what happens, it's the square of the 10, so that's 100, so it's 100 times lower. 8. Below 8. No, it's the other way, right? That's why I'm trying to get all you to correct me. I'm the absent-minded professor up here, and you're all my students saying, "What's that number?" So let's do it out. Everybody, you got paper? This is a real work session.
Well, I mean, does it even make sense? I mean, once you say 10C, that's something that I would just highly object to, that gamma formula may not be applicable at those speeds.
Well, when Einstein did that's the kind of question we want to bring up. When Einstein made the equations, I don't think he was concerned that it was 300 million meters per second. It could have been 400 or 500. Because...
Well, I think that definitely there was a limit stated, right?
No, he didn't state
a
a...
C squared.
Right.
And so when the V squared got equal to the C, there's something definitely happening there. So if you just throw an arbitrary constant in front of there like 10, then
well,
I suppose it would apply, but it would be 10C, so the point at which that would become 0 would be 10C as well.
Well, okay, but I can answer that in the following way. The V is assumed to be limited in its motion by C. The velocity of mass can't exceed C. Right? That's what you're saying, right? We're still in the universe, the mechanical universe.
Well, thinking about it, that just changes the point at which it scales. So at 10C, say it was like 300 kilometers, it would be 3,000 kilometers per second. So at the point at which you would have a problem, there would now be the V where it would become the 0, it would be 3,000 kilometers per second, not 300
right.
kilometers per second.
Okay, but what I want to go back and say is we don't change physics. Let me
Well,
finish
you
the
are
thought.
changing physics by suggesting there's a superliminal.
No,
Speed.
I'm saying I have this new form of energy that I can use to make measurements, nothing else.
Yes, and that would be a new form of physics, since we don't recognize that there's anything.
Yeah, it's right. It's a new form of physics.
I mean, you could just say there's a little green fairy and make and proceed from there. So,
Right,
I mean,
right. Okay,
mathematically,
that's
I think it's fine, but it is not anything
Right.
that we currently recognize.
We haven't got to the haven't got to the paradox part. Go ahead.
There are two forms of light. There's a transverse, which is what we've been talking about, but there's also longitudinal.
Uh-huh.
The equation for longitudinal light does not have a C in it. So the longitudinal light has infinite velocity. So there might be a possibility of making a measurement with longitudinal light and making a measurement with transverse light and seeing the difference.
Okay, so we'll remember that because it just says that even though I'm talking about now this 10C light, there might be a infinity C light, as you saw, that we can ask the question about again later on. Okay. But let's go back now and somebody, Ray, are you working this out?
I'll put it in Excel.
Yeah, put a V in and a C and give us a round number. What V happens to give us something over here?
Ken Bernhardt has a question. If you could somehow compress the ether, do you think that would increase the velocity of light?
And that's an interesting question. It's an experimental one. It takes us right into the empirical world. So let's find out. If I have, assuming ether is a carrier or a wave, and we just use air for, if I send air out and it tracks sound, I'll get the speed of sound at standard conditions. We know if you heat the air out, you get faster sound waves. We know if you increased the density of the air under pressure, you get faster sound waves. So the answer, I would answer that person by saying, using empirical experience that we have, density does speed up the speed of sound. However, with light, we get the reverse. If you take air and you increase its pressure, light slows down. If you then take it and take a very high density, things like glass, light slows way down. So we have two conflicting empirical bases to test this against. So I would not be able to answer. I wouldn't know without going.
Oh, I have one possible solution to that, and that is that regular matter contaminates the ether, making it less dense, actually. So the more regular matter you have, it actually reduces the density of the ether, which is one possibility.
Sure, and the lattice theory does the same thing. Yeah. So how you doing, Ray?
I'll bring it up.
Okay, you'll wave, Carl.
In case I didn't hear right, in case I didn't hear right, it's my understanding that if you have air at a certain pressure and you reduce its density so it's thin, then you would tend to decrease the pressure. But if you increase the pressure back up to where it was by heating the air, then the net effect is that the speed of sound through that thin but heated air is much faster. In fact, the speed of light through, I don't mean light, I mean sound. The speed of sound through hydrogen gas is, of course, extremely fast, assuming that it is at the same pressure as oxygen or nitrogen. That may be the gist of what you were saying, but I was afraid that I heard you say the reverse, that the thinness decreases speed of sound, and I don't think it does.
I got to check here with Ray. First number can't be right.
V over C, 1/6.
Yeah.
V is 6/10 the speed of light.
Right, but 1 over that has to be less than 1.
No, because 1 over square root.
Yeah, they both either have to be greater than 1 or lower than 1. So going back to what you said about the hydrogen and so forth, we can answer the person's question by saying there is a change, and we know that. And then whether it's one or the other, we have to look at the different parameters. Especially changing the type of gas from oxygen to hydrogen, that would be a massive change. Okay, so we're going to come up with 2 numbers, and I can work on it just by this to get started, and we'll come back and finish it up. So when Ray gets us an exact thing to use. Okay, we're going to find out that the gamma for C leads to, when Alice measures B, the B will be different here than it is here. B for the C problem and B for the superlight problem. We're going to get 2 different lengths that Alice measures B's measurement to be. Now where this the significance of getting two measurements is one of the contradictions, or one of the complaints, challenges to relativity that have been around for a long time, which says because you're using light as a measuring instrument and it has a time delay, and that time delay gets confused when the object you're trying to measure is moving, because if you send the beam out to here and back, when you send the beam out to here and back, this is moved, and the motion actually fouls up the measurement. So that challenge to Einstein's theory says that you're not measuring actual changes, you're measuring instrument error. Einstein codifies instrument error, is how that challenge comes up. And so I got this as the 1 meter. We'll also put the clock in here. All right, we got that clock, and we have the clock here, and of course these are shown as dial clocks, but there's super precision atomic clocks. But again, for B to be younger, when they come back, their clock had to slow down. But if you go the other way, this person says this clock slowed down. And what the relativists say that resolves the problem is that when they get together, somehow they're the same time. And that what Nick calls absolute time, or there's another one, proper time, that the clocks are always the same.
Unless the formulas are different, they are different.
Okay,
One is greater than one, one's less than one. Most formulas. Gamma is not defined. That's how you want.
I have a comment from Slobodan Nedic. He says they don't even need to use that high light speed to measure each other's objects. They are supposed to have individually synchronized clocks at each of points in their system, what actually emulates S equals infinity. I'm not exactly sure what that means.
I don't either. Okay, good enough. I'll use raised numbers. And I see what happened. I just always, I didn't realize you play around with this number and change its value to a higher C being something else, then, all right, so we're in good shape. This one comes out as a measurement of right. So I'm going to change it to square root of C squared minus V squared. It's got to be wrong. All right. So that's lower. He says that's 1.25, and this is 0.01, 0.1. Okay, 0.1. All they have to do is be different to get for the paradox to be true.
B over C equals to the 0.6 is what I use.
Yeah, so V over, for this thing here, we're working with V over C equals 0.6. Okay, 0.6. All right, but let's go back to the paradox, because the paradox is not the math paradox, it's a philosophical paradox. So if using a different measuring tool, we measure a different offset, and then I think using Bill's idea that there was a super light at infinite C, and if you plugged infinity in for C, then both measurements are the same, going both directions. And you get, if you can measure it infinitely, you're both going to say you have 1 meter. There's no shift.
if you use that type of radiation.
Yeah. I mean, if you have this fake radiation, you can just send it out there and measure them. Then there's no change. The change comes because the speed of light is limited, and you make changes in time and so forth, and you get different values for this if it's traveling and moving. So the basis of this paradox is that light becomes, according to this, an instrument error. And if it's an instrument error, then you can take Einstein's equation and actually use it backwards in the following sense and solve all the problems. If you can accept it's an instrument error, then when Alice makes a measurement on B and comes up with a number that it's shifted by 1.25, Ray, see, we know that it's got to be measured to be shorter. So give me the reciprocal of 1.25.
0.8. 0.8.
0.8, yeah. And so she makes this measurement over here and says it's 0.8, but she also measures the speed, and it says it's 0.6. If you then run the equation backwards and say, I measure 0.8, I run the equation backwards, I get 1. And we solved the problem. There's no more problem with dilation problems. You measure the clock rate by sending speed of light, you send a signal, and then you send another signal and measure how large it changes. You say, oh, this is slower than my clock by 0.8 if I use Einstein's equation, which is the same correction factor. You come back and the clock times is the same. And there's no more problems of people viewing other people's clocks the wrong way. They all get the same time. And so the paradox leads to a solution, but it's got to be accepted as a true paradox. So that's why I was bringing this paradox to you, to say, if we think we've discovered something new, then we should launch a project on it, which means on the forum at the society, involving everybody who wants to be part of this, and start to write a paper on what if there were this special measuring technique that was faster, what would it say about the theory of relativity? And then we would, based on that, actually write a paper from the society with a new paradox. Okay, we intend to do that. And that's what I'm saying. This kind of thing. So all the things you said, Franklin, when this starts, you want to put that in. You want to take what you said, think about it some, write it in there, circulate it to everybody else who signs up on the project. And they all look at it, and then it all goes in the hopper to try to figure this out.
And then does this really have anything to do with the original twin paradox? I mean, I'm thinking, well, that's interesting, but that's definitely not the twin paradox. So are we talking about something completely different, or what's your... I mean, this just look like relativistic corrections, which are frequently used in space satellites and such. Are we talking about anything different? I mean, let me see if I can summarize what you're saying. So you're setting up the situation where they're just measuring distances, and it appears that these two people will get, I think they would get the same measurements if they measured against each other. But you're saying that if there existed this 10 times faster type of emission, then you're saying the paradox that you're introducing is that depending on which type of light they are using, they would get a different measurement.
Correct.
And we know that that's not correct. So you're saying that that is basically an observational effect. You say instrument error. So I would kind of distinguish instrument error versus an observational effect. you know, for example, if I put my finger up in front of my face and I'm pretending to squish your head and I measure how big that is, that's only about half a centimeter, but your head is not half a centimeter, it's just, but if I went way up to your face and measured it, you know, your face would be like, you know, 10 inches long. And so is that a paradox? And I would say that that's just an observational difference, and maybe not a paradox. So is that? So I might not consider this being a paradox just because I consider it an observational difference.
Right, so let me reply to that, because the same, what you just said to me, is this a real paradox? We have to understand what the complaint of relativity is, what the objection of relativity is. And that is, the relativists say that if something is moving, real changes occur. The muons coming from space change their radioactive decay rate, so their clocks must really be running slower. Right?
Yeah, that's true.
Well,
We believe that's true.
Sure, except, but, and Bob, I'll come back because you can answer this. But if it's really a relative problem, the Maxwell's demon riding on the muons coming down is going to say, wait a minute, our clocks are not slower, your clocks on Earth slow down. And the relativists don't look at that. They claim things are all relative, but they only look at one side of the problem. And if you force them into the room, you get overwhelmed, and of course you can't carry on the conversation. What the paradox does is not give an answer. What it says is, you have to go back to the paper that Einstein wrote and really look at the words one at a time. And if you go again in the forum or in the newsletter, and somehow I'll get to anybody who doesn't have this, I published a small paper, which is just Einstein's 1905 paper, broken down by concept, like you would do in a legal brief. So it says, it starts out, it lists number 1, postulate 1. Number 2, postulate 2. Number 3, starting with a relative frame, that's number 3. I make the following claim, number 4, and you go, and each one is there so that when we discuss it, you can go back and say, according to the annotation, item number 3, 5, and 7, this is the conclusion. And people don't do that. They get lost in the final wording and don't go back to a line item by line item by line item.
Well, I like your initial description of the paradox. You said that, you know, Einstein's paper strictly dealt with, you draw a picture of the Earth and a single rocket going off.
Right.
And so that's what Einstein's paper deals with. And then you have these other crazy people who come in and throw in, they erase the Earth, like you showed, and throw in a second rocket.
Right.
So are those people crazy for doing that? Or is that something that Einstein actually said? Because what Einstein said was just your first picture, which is a rocket coming off from the Earth with the arbitrarily picked frame.
Right. And the answer to that is, if you go down about 2 paragraphs before the end, that's where he throws his zinger in. He said, based on what I said, if there is absolutely no way to say what is rest in the universe, then we have to be able to take everything I said and reverse it all, and it all has to work the same way. And he also told people on the side, remember, when I published this was a fad going around, that the speed of light was constant with respect to the observer. He said, this is total nonsense. It can't possibly be, because if it did, all physics gets turned on its head. I just wrote it as a negative proof. I said, let me start out by saying the speed of light is constant with all respect to all observers as a postulate. And also—
Yeah, but Einstein never said that.
Yeah, he did.
No, that is my main point, which is if you read the second postulate, it says any ray of light moves in the quote, stationary system of coordinates with the determined velocity c, whether the ray be emitted by a stationary or by a moving body. So
Right.
he's saying that even if the body is moving, it is going at the velocity c
In a
in
station.
the stationary system of coordinates.
Right.
So that is not saying, this is my claim, that is totally not saying that the speed of light is constant in any frame of reference. It's only constant in the stationary system of coordinates,
Yeah.
which he states there.
Okay, and that's what happens over and over again. You've hung on to one line.
No, that is the most important line. There's a big difference.
So you changed it again.
No,
You said
there
that's
is
the
a
most
big
important
difference. I mean, I'm reading directly
From
from
the paper.
Einstein's paper.
Right.
He does not say that the speed of light is constant in any reference frame. That is utterly wrong.
line. Okay, so now everybody got that?
It's inertial.
No, hang on.
Inertial.
No, hang on, I'm making another point, and then I want to go back to Bob, because he's had his hand up all the time. We are not arguing about the mathematics or the physics. We're arguing right now between Franklin and I, whether both of us can read English and have read the paper and used all the pieces in the paper. It's not about the math. It's about interpreting words and being comprehensive about what's in there. So I say, right now, what I would say to Franklin, we should not be sending emails back and forth debating this. We'll both go to my annotated Einstein and say, based on this one, this is where Franklin got his first statement. Based on this one is where Einstein says, but everything I wrote was just to establish the first analysis. It should all work in reverse, which is in the paper. And he would either be able to say to me, Bruce, it's either there or it's not there, right? And if it wasn't there, then I would say, I accept that. I made this up in my mind. He never made that second statement. But now we'll take on a new way. If he said it only works in the absolute rest frame, now we got to find him. Right. Let me go to Bob, because he's been trying to ask a question.
Well, maybe I shouldn't do this because it involves the.
I can't hear you. You have to hold it and turn it on.
Okay, no, it's on.
Yeah.
Unfortunately, this is specific to Dave and I's particle model, but it's based on the fact that Newton suggested there's a force that causes objects to move or bend, slow down, speed up.
Go ahead.
And when you look at refraction, you're seeing light bend. So we're suggesting there's a force that causes light to bend, and that's faster than c, which supports the 10c or in fact greater. It's just a comment.
Well, that's interesting, because one thing is to do this as a theoretical one. One is to later on have somebody come back and do experiments. The experimentalists. So that's interesting. Carl.
Well, the experiment.
I mean, Bill.
The experiment, this is Bill Lucas.
Yeah,
The
Bill.
experiment that's been done is you make a muon in an accelerator and it decays. And so you look at the half-life when it's sort of at rest, and then you accelerate it and you see the half-life changes. And so they say that's a relativistic correction. But you could also have another argument on what's happening, and that is as the muon moves faster, it changes its energy, and that changes the binding, which causes it to live longer. So, but anyway, so you have relativity theory, which is not a physical theory in the sense that it gives a physical explanation, but it gives a mathematical explanation. But in the other case, you have a physical particle that its binding and mass, or whatever you want to call it, changes with the velocity that it moves, and that causes it to have a longer life.
Sure. And what you're saying applies to almost every experiment that's been done as evidence for these equations, essentially the Lorentz contraction.
Right.
And The other one is the Kepler-ness, when they flew the atomic clocks around the world on the planes. Yeah, that thing, that experiment, people have gone in there and found out they made a sign error in transposing their data. Because they actually, you can get the data and look at it, and then when it gets transposed into math, there was a sign error. And if you take the sign error and correct it, it finds out it duplicates GPS and says there's an ether, but it's somehow bound to the Earth, close into the Earth, and we've never done an experiment far over. And everybody must know that Michelson-Morley has been torn to pieces. And even so, you read all the time in the news media, oh yeah, Michelson-Morley found null result, zero velocity, and there's never been zero velocity in any of those experiments. Yeah.
There's different theories as to what the ether is, but if you have the theory that the ether is the electromagnetic field and that all particles are solitons that are made from the field, then at the Earth, the solitons, the fields attached to the solitons extend a certain distance into space.
Mm-hmm.
And so you won't find an effect due to the rotation of the Earth quite the same, or the velocity of the Earth, because the velocity, the ether is traveling with it locally, but there is an ether farther away that's not traveling.
Sure. Okay, and again, we've got the empirical stuff is suspect, and that's why I say if you go into the forum, there's a reference section. That's the first, that lists the Sapir-Whordy and all these other papers that I collected, or that she collected, 1,300 papers, all saying we're not getting the right answer here, not getting the right answer here, and that's why the whole relativity thing is still up in turmoil. Yeah.
It seems to me.
Bob, can you grab a microphone for him? Thanks.
It seems to me the paradox you're creating is because you're just comparing two things. If you take three things, one man standing on the bank, one man on a train, and one man flying, and then you take the interrelationship, neither one of them would be able to tell if they're in a cell which of them is actually moving.
Correct.
But the fact is there's relative speed between all three of them.
Correct.
One is going slower than the other. Consequently, there is no paradox.
I'm trying to say that when you say one is going slower, you mean with respect to the Earth?
No, with respect to each other.
Oh, yeah.
Yeah. If you take three instead of two, yeah. I don't know if I'm going faster than you or you're going faster than me.
Right.
But if we take three, then we can say, okay, all three of us think the other one's moving and we're not.
Right.
However, when we look at the difference between 1 and 3 and 1 and 2, we realize that there is one object is moving faster than the other.
Sure.
And if one's moving faster than the other, one is aging slower than the other.
Well, you could say that one is, so to try to get that I understand, we have somebody who says I'm going 0 because they're standing on the ground. Then we got the train is going 20 miles an hour, and then we have the plane that's going 200.
Yes.
So what we can say is that between these two, this one's closer to this one than this one. So that I agree with that, right? That's what you were saying. But, and we can also agree that this one's going faster than either one of us, so we have that. But if, in a relative sense, if these were supposedly, we then move them away from being on a platform and using Earth as a reference. If we just take these three trains and these three things and make them planes, this could be a balloon, we don't know. And we don't know now, have a ground reference. Then, in fact, what would happen is, you would ask this guy what the other two are moving, and that person would say this and this and this. But if you ask this one what's going on, He'd say, well, this guy up here, from his standpoint, let's go 0. So he's saying, I gotta figure out how to do this, from the standpoint of 0. This is what's happening. From the standpoint of 20, he thinks this guy is going minus 20. He's going 20 in the wrong direction. And I'm going 0 with respect to myself, and this guy's going 180. From the standpoint of the 200 guy, he's going to say he's going minus 200. And he's going minus 180. And I'm going 0. And if they can't tell it apart, then you have to say, how do we interpret all this? Now, if we don't take relativity, if we say we can make instantaneous measurements and we use Newton, basic Cartesian coordinates and stuff to make this, that's not a problem because we all realize we're all moving. So doing that, we can say, well, what's the question? You want to know how he's measuring things here? We could calculate it and everybody gets the same answer. With relativity, you can't get the same answer because it's a square law and it follows up the ability to calculate back and forth. Franklin's got a, hang on, have an answer?
We've got some comments from the live stream, so we appreciate
Okay.
the 10 people who are watching right now.
All right.
We've got a comment from Frank Senatora. It says, doesn't Doppler effects into the ultra blue have an effect on how you handle the analysis and measurements observations?
So by Doppler, he must be talking about redshift
Yeah, probably.
because
When they're coming at relative to each other, you shine light at each other, that's going to change the Doppler will change the frequency.
right, because again, if he says, as soon as he said ultraviolet or ultra blue, we're talking about light, not sound. I just want to get the physics. And
So we had an additional comment from
well,
Frank Woolman.
let's try to answer his question.
Yes, go ahead.
Which is again, what's his question about the ultra blue?
Well, the question about the ultra blue, once again, was doesn't Doppler effects into the ultra blue have effect on how you handle the analysis and measurements? That's his question.
Yeah, and there's a lot of ways to answer. I mean, one is you have to ask what kind of instruments can measure into the ultraviolet. Do we have any knowledge that the velocity of light is dependent on wavelength and is faster in the blue, or is it slower in the blue? Faster in the infrared, slower in the infrared, faster in the wave, the radio waves. And so far, I have not read any, but I've heard people over dinner discussions saying, "Oh yeah, it's not exactly the same." If you do it in a void, supposedly you get 0. But as soon as you start involving anything else, like density of matter, like glass with light, the velocity changes all over the place with density. So I hope I've answered that question. The answer is yes. If you do it in a void, they're the same. But if you get into any kind of material, they're different.
He has some additional comment. He says if Einstein's special relativity is faulty, then there is no paradox. And Slobodan Netic says, none besides Engelhardt understands the so-called third Einstein's postulate, the contradiction between the method of individual systems clock synchronization and the subsequent LT relationships.
Yeah, well, that's fine. Slobodan, thanks for listening. He's in Slovakia, I think. Yeah, write to us on the email list about that question. Go ahead, Bill.
I was going to comment, if we have an ether, we talk about entrainment, and the part of the ether is attached to the matter. And so then the question is, well, what is dominant? So for instance, if we make a measurement on the Earth, is the Earth dominant? Or what is the contribution of the sun? Because it's much more massive than the Earth. And so you've got to take that into account. So if I do an experiment where I have two people go away and come back, but they're both on the Earth, I'll get one result. But if they go out of the solar system and come back, I will have gotten out of the entrained ether and come back. I'll get a different kind of result. But it's the same experiment. It just
Right.
has to do what is dominant in terms of the
Sure.
ether.
And so that's an important point to bring up here. GPS has already clearly shown that the speed of light changes with gravity. So they have to take that into account. They have to take into account variations in Earth gravity going over a mountain. It's that sensitive. Or an ocean, right. Right on the Earth. And the tides. And so GPS is corrected at the rate of 1,000 times a second for every satellite differently, depending on where it is. I mean, so gravity affects all over the place. Gravity of the moon comes into it, gravity of the sun comes in it. It's also affected by the density of the atmosphere and the humidity, and they correct for all that stuff. The important point of this whole paradox stuff is that Einstein rules all that out. In other words, in his paper, he just starts out with the assumption, we're in the void. We're in the imaginary void of space, so let's just use basic mathematic principles for a simple problem. And so once he gets into there, what you can do with very simple math is say, if you had a moving observer and a source of light, and the source controlled the speed, you could tell. If you were, very simple thing, and this is what's the three basic models we're using for the problem on the CMPS problem, right, that we're studying the project. The second one, if you have a moving person in an ether across a ground plane, you can tell. And if you have a light being determined by the observer, and the observer's moving with respect to the transmitter and the ground, you can tell the three. And so once the project gets the three models set up, we now have enough sophisticated on instruments, we could easily put them in a plane, two planes flying and get the answer. But we don't have to put them on planes, they're already in the GPS. And the GPS is going to come up with an answer. And we know what the fight is going to be, because it's the same one as before. The relativists are not going to agree with the models, and the data people are going to say, we don't want to get involved in this. Yeah, okay, good. The data people are going to say, we don't care what you believe, we just adjusted it, we get the right answer. And what I'm hoping to do is to, in our paper about this, is to describe the errors in the words. And you know what Franklin said is got to be one of the major topics is to say, can you take Bob and Alice and reverse them? Can you take away the Earth or the rest frame from Einstein's paper based on what Einstein wrote? And this is it's just us using English words. And Franklin will get in and have his chance to post in one of the memos. I think we're running close to the end, but
Right, well, that's what I was going to say.
okay, he's done. Thank you.
Yeah, we have really have to cut it off here. So thank you very much.